The inclined plane. You see a lot of problems in physics textbooks that deal with an object on a ramp or an inclined plane. A skier going down a slope is a classic example. They'll ask you to figure out the forces that act on the skier, although no skier as he goes down the ramp, down the slope is really thinking about that kind of thing. But being able to consider the forces that act in two or more dimensions and find their components and figure out your way around that kind of thing becomes very important if you're going to be building buildings, for example, or bridges. Civil engineers and architects have to be concerned about the forces that act on the steel frames that hold up their buildings. Here, for example, we have here a steel girder connected to a bigger steel girder on this big frame here. At this point here, where the two are connected, it's very important to know just what kind of forces are going to be acting along this beam that might break the rivet there, the connection, or perpendicular to this beam that might cause the beam to bend and buckle. And so architects and engineers need to be aware of this and sure that the building they put together is strong enough to withstand the forces that are going to be acting on it. And understanding complicated systems like this big thing starts with understanding two-dimensional forces of a block on an inclined plane. So if we consider this situation that we have here, and we have a box sitting on a ramp, and here on planet Earth, as ever, its weight is going to be pulling it down. So we can draw a vector there that represents the weight of the object, and we can calculate the weight, its mass multiplied by acceleration due to gravity. And the force that prevents this block from falling through the ramp is the support force, which is also known as the normal force because it's perpendicular to the surface. So it doesn't act up and down, it acts at 90 degrees to the surface. It's off in this direction. And if we think a little carefully about this, in the absence of anything else, if it's a frictionless surface and there's nothing else to hold this block up, it's going to start accelerating down the ramp. In the absence of anything else, we're going to have an acceleration down the ramp, which means that there would be a net force acting down the ramp. So we've got a natural system of coordinates for this block. We can have our x-coordinate parallel to the ramp and our y-coordinate perpendicular to the ramp. Okay, so x parallel, y perpendicular to the ramp. And so if the net force is down the ramp and the normal force is up that way, basically the two forces that are actually acting are the normal force and the weight, and the resultant of those two, if we apply the third P, the parallelogram rule, to the support force and the weight, then the resultant of those two gives the net force that's going to cause this block to slide down the ramp and accelerate. So we have here this parallelogram with the normal force, the support force from the surface pushing up that way, the weight pushing down, and the resultant of those two is down the ramp, and in the absence of any other forces is going to cause this ramp to accelerate, this block to accelerate down the ramp. And that's a non-equilibrium situation. In the real world, we don't get frictionless ramps and we don't get frictionless boxes, and you can often see a situation where something sits on a ramp and doesn't slide down the hill. This is really important if you've got a really nice car, because when you park it on a hill, you don't want it to roll down the hill, you want it to stay in one place. And friction between the tires and the road is what holds it in place. And so if this block is going to be in equilibrium, then there's going to be a frictional force which acts up the ramp in this case to oppose the motion, or the other two forces and the motion that they would cause. So that this line and this line are equal. And then we have the idea of equilibrium on an inclined plane. Friction back up the ramp, the support force up and to the right perpendicular to the surface, and the weight pulling down. Those three forces together should be balanced. And what that means is that any two of them added together should make the third. We've already determined that the normal force plus the weight gives this force down the ramp. And if it's going to be an equilibrium, then the friction has to pull back up the ramp. In addition to that, we can also apply the parallelogram rule here to add the normal force to the frictional force, and we end up with a vertical force here. This force here is equal and opposite to the weight, so that there's no acceleration up or down. And finally, because it's not jumping off the ramp or falling back down through the ramp, we could apply the parallelogram rule to the frictional force and the weight, and the vector sum of those two, if I draw that in, is down here, and it's equal and opposite to the normal force. So any two of these forces, if I make the forces themselves a little stronger, the lines a little thicker, any two of these forces added together using the parallelogram rule is going to give us the third force. So we've got x parallel to the plane, y perpendicular to the plane, and then we can apply the parallelogram rule to add any two vectors to find the third, the 3p rule.